Now we'll talk about something called the center of mass of a object or a system. Okay, let's look at this. So if you toss a baseball um, and a base bat and baseball bat, now you can see that none of the points on the bat go on a parabolic trajectory. There's only one point that goes on a parabolic trajectory, and that point is called the center of mass. Okay, that would be the point. If effectively, if you squeeze the entire baseball into a point, that's the point you want to squeeze it at. Okay, so that's the center of mass, and now we'll learn how to find the center of mass of objects. Okay, and again, I urge you guys to go to these URLs and look at the center of masses of various systems. Okay, so if you have an object in real life, if you want to find the center of mass of an object, so just hang the object from a point, the center of mass is somewhere on that line, and then hang it from another point, and so the center of mass is at the intersection of those two lines. And now, of course, if you have a three-dimensional object with an odd shape, you just have to hang it on 3 points and find the intersection of those 3 points, and you'll get the center of mass. Okay, so now if you want to find the center of mass of a system of particles like this, these are point particles, or they can be also extended objects, but you know the center of mass of each of these objects. Okay, so what we are seeing here is the center of mass of these three objects is right there. So you see the center of mass can be outside the system of particles. So there's the center of mass of these three guys. Now what is the x and y coordinate of the center of mass? The x coordinate of the center of mass is each mass times its x coordinate, the center of mass of its coordinate. So m1 times x1, m2 times x2, and x3 is 0. So each mass times the center of x coordinate of the center of mass of that object times the total mass divided by the total mass. So that's the x coordinate of the center of mass. Similarly, the y coordinate of the center of mass is given like that. And in three-dimensional equations, the z coordinate of the center of mass is each mass times the z coordinate of the center of mass of that guy divided by the total mass. So that's the center of mass. Now if you have a continuous distribution, the summation signs get replaced by integral sign. So there's the total mass of the object, x coordinate. What you do is you take this mass and break it up into little pieces. That's dm. Okay, and so you do this integral to get the x coordinate of the center mass. Similarly, the y center mass is y coordinate of that little piece divided, integrated over that, sum over all the little pieces, and divide by the total mass. So that's how you get the center mass of a continuous distribution. Alright, so here's the Fosbury law. So this is to illustrate the falling factor. Okay, so let's say here's ground level, here's the pole. Now what this diagram is, if you go over the pole like that, what you're doing is you went over like that, your entire center of mass went over the pole. So you raised yourself up to that height. And most athletes roughly, I mean all elite athletes can roughly go or jump the same height. Now on the other hand, if you go over the bar like this, what has happened is, okay, so we'll draw the same diagram. Okay, so here's the pole. Okay, and now when you fold yourself up like that, what has happened is your center of mass is going under the pole. Your center of mass has risen only that much. So with this technique, you could actually clear a pole that is much higher. Okay? And so Mr. Fosbury invented this technique, and so it's called a Fosbury flop. And so now doing that, you can see that the center of mass, here called center of gravity, for our purposes it's the same, is going under the pole, okay? And so physics is useful. So again, the system of particles, so if you have a system of particles, like we already said, if that's the force acting on that, that's the force acting on this is the force acting on this, the sum of the forces acting on all the particles is the net force, and that is equal to the total mass times the acceleration of the center of mass. So Newton's second law becomes as if the entire mass of the system is at the center of mass, okay? So the acceleration of the center of mass is what comes into play, okay? So so in this example, here's a shell, and the shell is launched and is only going under the influence of, traveling under the influence of gravity, and it's going on a parabolic trajectory. And let's say if it explodes into 100 million pieces, even after the explosion, the center of mass will still be going on that original parabolic trajectory. And that's what this thing shows. So for the system of particles, that's the total momenta of the system of particles, just the sum of individual momenta. And Newton's second law applies, as we said before. The net force on all the particles is equal to rate of change of momentum of the system of particles. All right, let's pause now, and then we'll talk about rockets.